Okay. Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good morning.
Good morning, doctor.
Okay, 54 students. Okay, Alhamdulillah now. Good morning. Good morning to everybody as well. So I hope another 2 more students. Okay, let me another prepare the punching. So academic. Okay, one moment. QR code. QR code here. Okay. So real analysis courses. 2 hours. Okay, now let me open. So how many students? As 2 more students. 57. Still not all. Okay, I hope at the 15 minutes, I hope they will log in. So now let me share and you sign, register. Please, then I have to do. Okay, please. Register. Okay, have you done? Okay, I hope you have done it. So now let me open my whiteboard. Okay. So, okay, let me give the end. How many students? Here. So 58 students so far. Okay, after 1 hour, I will give you to punch in again. Who are not able to do, they will do it. So now let me record. Bismillah. Okay, now it is recording. So let me share the screen. Okay, now today we will back to the main lecture notes. Okay, we will back. But before going to the back to this continuation of the lecture notes 1, actually I want to revise a few of the important issue, how we prove the statements. Okay, there are very nice and few problems. I think we can We can solve one question from here and one question from here. Okay, this is the for the equation, and this proposition. Where is the proposition? So A over B. Okay, I hope here. Okay. There is, you see, there are many preposition, right? So here you see 2.1 preposition for non-zero positive real numbers. A square always positive. How to prove? There is a immediately proof. But for preposition 2.2, 2.3, 2.4, and so on, there is few of them approved. Okay. For example, how we can prove using the axioms, because most of these prepositions can be proved by using 11 axioms. Okay. So how to apply? I just show few of them. Then we go to the main topic from our lecture notes. So okay, now we have enough space to write down. So proof. Prove the proposition. So once preposition, actually we should prove it. Only axioms we don't prove, we just accept it. So that's why please pay attention. Preposition, theorems, lemmas, corollaries, or must be proved. So the just one of them, if A less than B and B less than C, then A less than C. How we prove? Now look at proof. Very interesting and easy. Since A less than B, I can easily say B minus A is positive. Since B less than C, I can easily say C minus B is positive. If we have two positive numbers, then their summation B minus A plus C minus B, C minus B actually is positive by the axioms. Positive number. So the summation is positive. So from here, I can see that if I open up B minus A plus C minus B greater than 0. So this B minus B is 0. 0 adding to the n numbers is 0. So from here, C minus A is greater than 0, which implies C is great, or A less than C, or I can say A less than C or C greater than A. Okay, so both is A less than C, or I can say, or C is greater than A. So you see, C greater than A implies this. So you see, by using the preposition, the axioms, we can prove it. For example, here, how we prove, for example, this preposition 2.4, preposition 2.4, for example, C greater than A, this. If A is greater than 0, okay, A greater than B and C greater than 0, then A times C is greater than B times C. So or C greater than 0, C times A or C times B. Okay, on the left side, on the right side, doesn't matter. So we have to prove this. Proof. So what I do, so since A greater than B implies A minus B is greater than 0. Since C greater than 0, then you see, this is A minus B greater than 0, C greater than 0. According to the axioms, I think the last axioms, 11, their product is also greater than 0. If we open up by distribution law, this one is equal to CA minus CB greater than 0, which implies CA is greater than CB. You see, if A greater than B, C times A is greater than C times B. I proved this. C times A is greater than C times B. But please pay attention, for every case, we have to state this one, axioms, for example, 11, axioms 11, because of axioms 11. And this one, the product, yeah, A minus, if A greater than B, then A minus B, no, not 11. This one, I think 10. Huh? This one 11. Axioms 11. So it is like this. This is distributive law. If I'm not mistaken, distributive law is axioms 1, 2, 3, 4, 5 or 6. 5. 5 for the product, 6 distributive law existence. I think this 6, axiom 6, and this one implies once it is greater than 0. You see, here we need to put like this, because this axioms, and if this one axioms 11 again. Okay, I think this is more proper proof. Okay, so please exercise all this type of things. You know, I will give in the because I think next week we can make it the this week I will finish the chapter 1, and next week I will give the first quiz. Is it okay? So I hope it is okay. So now you see any other prepositions also can be proved this way, and here another this preposition also can be used. Huh? So here another interesting point I want to show you, arithmetic geometric mean. Also this is very interesting point. You see, arithmetic geometric mean is not greater than arithmetic mean. Okay, using this, how we can prove this kind of this example is already has solution. Okay, arithmetic geometry in general, here also there is a solution. Okay, exercise. Okay, so this solution, when you learn it, then you can understand how to prove. Well, for example, this exercise 2.3, just one exercise 2.3. Okay, given x, y, z are positive real numbers. Okay, x, y, z all strictly positive. If positive, strictly greater than 0. So, for example, how to prove if x plus y is equal to 2, then x, y is less than or equal to 1. Okay, now proof. Proof. We have this formula, geometric mean AB is less than or equal A plus B over 2, arithmetic mean. So I will consider xy, it is less than or equal a plus b, x plus b, not a plus b, x plus b, x plus y over 2. X plus y is equal to 2 over 2 is equal to 1. You see, x times y equal to 1. I prove it. Okay, one more, the number 3, because this is interesting. And you know, if here it is said, if x, y, z, this triple product is equal to 1, how to prove that x plus y plus z should be greater than 3, the summation. So now here we do opposite. In the proof, we start proof. We start this x plus y plus z over 3. Arithmetic mean is greater or equal to arithmetic mean x, y, z. And x, y, z equal to 1. Square root of 1 is 1. So this one, not z, 3 arithmetic mean. So from here, x plus y plus z should be greater than 3. You see, very simple, but very interesting. Okay, please do the combination. And one example from this equation also, actually, because equation so far we usually directly solve, but actually how we can solve. For example, the exercise 2.2, just one example. 2.2, for example, first one. 1 less than 2x minus 6 less than 4. Find, the problem is find x for the following inequalities. So what kind of x satisfies this inequality? So solution, now here not proof that this is a solution. We consider which one? The first part, 2x minus 6. If it is like this, then according to the what we call it, from here I can say 2x minus 6 minus 1, you know, I'm shifting this is to the this side, is greater than 0. Okay, so according to the axioms, you know, 11, if a less than b, then b minus a is greater than 0. So this one I shifted to the left and say greater than 0. Now if I simplify, this one will be 5 greater than 0. Now I will add both sides 5 to x minus 5 plus 5 is greater 0 plus 5. So this one is 0. Yes?
Negative 6 minus 1 is equal to
Sorry,
negative
sorry.
7, right?
Thank you, thank you. This is 7. Yes, thanks. This is 7. And minus 7, I will add 7 both sides. Okay? So now this one becomes 2x because this is 0, and this one greater than 7. So if now what I do, I multiply. You see here, I will multiply 1 over 2, which is greater than 0. If positive number is multiplied both sides, inequality doesn't change. So 1 over 2 times 2x is greater 1 over 2 times 7. So with this one 2 to cancel, x is greater than 7 over 2. Okay, from the first part, I got this answer. Okay, now from the second part, I will get the second answer. 2x So now 2x minus 6 less than 4. Less than 4. So as usual, 2x minus, actually we always try to get the positive, you know, because here I will say 4 minus 2x minus 6 is greater than 0. If I open up, 4 minus 2x plus 6 is greater than 0. So minus 2x plus 10 greater than 0. Now I will add uh, minus 10, both sides. I will add minus 10 on the left side and add on the right side, minus 10. So this one minus 2x plus 0 and greater than minus 10. Minus 10. Now look, I will multiply minus 1 over 2, which is less than 0, both sides. In that case, it is the opposite. So here becomes x. This inequality becomes less. 10 over 2 is 5. 5. Now I put the both solution in the one line here. I think better we can see. So somewhere we have 0. 7 over 2 is actually 3.5. 1, 2, 3.5. This is 3.5. So this one is greater. This is the solution space for this part. And this one, 3, 4, 5. 5. The solution space is like this. Now from here I can see x belong to 3.5. Strictly inequality we have, so therefore this doesn't 7 over 2 until 5. 5 is also not in. So in order to check the correctness, just I will take 1 point. 1 point from here, okay, from I. If I say this I, so when x equal to 4, look, 1 is less than x equal to 4. 2 times 4 is 8. 8 minus 6 is less than 4. Yes, it is correct. This is 2. 2 is greater than 1 and less than 4. So the 1 point in this interval satisfies this inequality. So it means any point in this interval satisfies this equation. Okay, here I do little change, and you immediately please now let me rewrite the solution space. So the solution space for this equation, for the first equation, is from 7 over 2 and 5. Okay, this is a subset of R in the subset. For example, if I do change, find a solution space of this equation, 1 less than 2x minus 6 less than 4 in integer number space. Okay, find the solution space of this inequality in natural number space. So in that case, after all solving, what is the solution space? Who can tell me from, look, this is a solution space, but it is in R. If I search solution space in natural number set, what is the solution? From here, integer solution space of this. Hello? Please tell me. Solution space of this equation in integer number set, not in R. What is the solution? How many?
So 5,
Yes.
is it 4 and 5?
X equal to
You
x equal
mean
to what?
integer? You mean in n only, right?
N is the integer number set. Yes. Starting from
Then
1,
will
2,
be
3, and so on.
1, 2, 3, and then, yeah, 1, 2, 3 in integer.
X equal to
Do you mean
1?
integer or natural numbers?
Yes, yes. We are switching solution space of this equation in a natural number set. Do we have solution?
Yes, only 1, 2, 3.
Which one?
1, 2, and 3.
1, 2, and 3.
Yes, or natural number set.
So you are saying that these three numbers satisfy this equation,
Sorry, including 4.
including 4. Okay, including 4. So any other suggestion? Now our friend is wrong. Okay, this is not solution space for this equation in natural number set. This is wrong. Any other suggestion? Please you look. But you see, the proof is the same. Is the same like this. You have to do all the procedure and get solution. I am just asking you to pay attention. This is a solution set in R. Now I am switching solution set in natural number set. So how many natural number
I think
exist
4
in this
and 5.
interval?
Is that 4 only?
Only 4. Yes, only 4. You see, only 4. So this equation has only one solution in N. Understand? Understand or not?
Doctor, why 5 not included?
Because inequality, on the left, on the right, there is no equality. So that's why it doesn't include. If one of them include, then one of them, of course, include in the set. You see,
Understood.
for example, if I get like this and get like this, then solution set of this equation in the end is not only 4. X equal to 4 and 5. Okay. The last question, if I am asking, find all the solution of this find the solution of this equation in Q, which is rational number set, rational number. So what is your answer? Rational number set. What about your already we have, I hope this is correct, nothing wrong. 7/2 up to 5. This is the correct solution set. So what about rational solution of this space? How many rational numbers we have in this interval?
7 or 2.
We have only 1, 2, 3. How many do you think? You see, so that's why, what kind of solution we are looking for the equation is very important. You see, I can easily what we call it lead you in the wrong space if you don't know the solution space. So for this case, pay attention. Please just try. How many rational solution exist in this interval? Okay. What about, for example, 7 point is not included. 7 point actually is 3.5, right? 3 point, for example, 6 is a rational number, is in here. 3.7 is in the, am I right? 3.8 and so on up to 4.9. What else? Do we have some more or only this?
Some more.
Yes, some more. Very good. What else? Can you give some? 3.61,
6-1.
3.71, and so on. 4.91. What else? 3.62, and so on. Actually, we have infinitely many sets. You see, infinitely many sets in this interval. So only here I should say x belong to the Q. Here x belong to the Q. This is the solution set, but we have to choose in this interval only for rational number set. For example, I cannot choose x equal to square root of, for example, 9, 15, for example. 15 is a rational number, lies here. It is lies. It is lies here. But it is not solution. Okay, it is not solution because this is not rational number. Understand? So that's why please look at the problems in the equation. It is we are searching the solution in which set. Okay, very important. You see, in the natural number set we have only one point, only one number is a solution, no more. But when I extend Q, we have infinitely many. But you can see, 3.6, 3.7, and etc. Zero, for example, is 3.601, 3.02, and etc. Actually, we have infinitely many solutions. All the rational numbers lying in this interval is the solution of this equation. Okay? So this is the tahlil or analysis of the solution. Okay? So since here there is no any significant requirement or special requirement for this equation, we consider x belong to the R. We are searching all the solution in R. So if I do change, please pay attention. This is the analysis of the solution. Okay. So please do revise this one very well. Next week, I will, definitely choose one of problems in here, maybe but only 2, 3. I won't get too many questions because it is a quiz. So, but here, very interesting, exercise. How we get, for example, this if the numbers the summation of 3 numbers is equal to 1, how we get this inequality greater than 9? Just we use geometric series and algebraic series. The inequality, arithmetic and geometric inequality. In general, please pay attention. This is the arithmetic mean and this is the geometric mean. You see, arithmetic mean always greater or equal to geometric mean. So using this inequality, we can prove many interesting phenomena or problems. Okay, please pay attention. So that's why this is the first part of my revision class for today. And now we go to the. Do you have any other questions here? Did you try to solve? Please, I don't check all the problems. I will check only half. For example, if you choose 1, 2, 3, 4, okay, including 5 because here 10, I can check. But this part I won't check because this one I keep for my examination. Okay. So please try. I like this lecture notes very much because too many good info, you can find it, and inequalities, you can see it, and there are a lot of good examples and exercises. Okay, please exercise. If no questions, I just go to our main lecture notes and start from here. Is it okay? I hope
Okay.
okay, because when you keep quiet means everything is clear, huh? No problem. If you are not trying yet, but still, I hope you understood the problem very well, because it is easy so far, very easy. Now little bit getting problematic, little bit difficult. What you call it? Actually, it is not difficult, but writing skill is a bit difficult to understand. But after reading, I hope you can understand. So now, natural numbers, integers, and real numbers. Rational numbers, actually, not integers. Natural numbers, integers, and rational numbers. Okay? So this is the first part of the topic. So I can make a little bit bigger. Why is this? So when I make it like this, okay, I can make it a little less. Okay. Can you see? I hope you can see, huh? Because this one making a little bit. Okay. Now, natural number set. Actually, you know what is a natural number set, but the proper definition is here. Okay. Proper definition is here. Natural number set. Natural number set. So now definition says, pay attention. A subset A of R. You see, A, capital A is a subset of, when we call it subset, we write like this. It is a subset of R. Is call it inductive. Is call it inductive. This is, please pay attention. A lot of time we repeat inductive. It is call it inductive if two conditions. If one belong to the A, and if some A, small a, belong to the A, then A plus 1 is also belong to the A. You see, any set satisfying these two properties is called it inductive. Is called it inductive. Okay, for example, natural number set is the inductive set. Integer number set is inductive. A rational number set, can I say it is inductive? I think can, because A is a rational number. If we add a rational number plus 1, because number 1 is also a natural number, integer number, and rational number as well. So rational number plus rational number always belong to the A. Yes, we can say inductive. Rational number set is also inductive. Okay, so this is the general definition of inductivity of the set. So the collection of all inductive sets denoted by I. You see, please pay attention. This capital I actually is a collection of all inductive sets. We see that I inductive sets, the collection of all inductive sets, is not empty. It is correct, because at least one element we have to be inductivity. Any set must contain at least one element, one. So it is not empty. For it includes R. We see that I is not empty, and it is a subset of R. Furthermore, the intersection of any collection of inductive sets is inductive. This is the second properties of inductivity. Intersection of any collection of inductive sets, intersection, also is inductive sets. For example, is the example we can understand more properly. So it is said that intersection, let's say capital N is a natural number set, 1, 2, 3. We will come to this. And for example, Z, we know it is an integer number set. From minus infinity, minus 2, minus 1, 0, 1, 2, and etc. So now if I consider intersection of these two sets, it becomes N. N is inductive. So if N is inductive, you see intersection of any, therefore intersection of any collection of inductive sets is inductive. Okay. For example, to confuse you, I will give like this. Take, for example, is a finite number set 1, 2, 3, 4, for example, and take B as 1 over 3, 1 over 4, 1 over 2, and 1, for example. What about intersection of these two sets? Can I say this this A and B is inductive because this one rational, the subset of rational number set, this one subset of integer set. Now intersection, you can see intersection is 1, only one element. Can I say it is also inductive? A is inductive, B is inductive, A intersection B is inductive. Can I say?
No.
Yes or not?
I think can.
You see, so some of the students says yes, some students says no. You see, that's why please you try to understand what is the inductivity. Inductivity says if element 1 is in the set and element of A is in the set, then A plus 1 is in the set, then it is called inductive. So this inductivity actually implies infinitely many sets. You will take any A, then add 1. You will get the element of A. Take another element A, take add 1. For example, A equal to 10 plus 1 is in the set. Another N equal to, for example, 1 over 2 plus 1 over 3 plus 1 is in the set. So this actually, these two inequality, two important properties actually leads to the infinitely many sets. It cannot be stopped at the finite one. Finite set is not inductive set. This one also not inductive set. Definitely intersection is not inductive set. Understand? To be inductive set, it must contain infinitely many elements. Understand? So that's why here it is said, okay, inductive. Now we define the set of all natural numbers as the intersection of all inductive subsets of R. Look, did you see in other literature that N can be written like this? No. Here, you see, because of the this definition, intersection of any collection of inductive sets is inductive set. So that's why. So we can consider the natural number set as an intersection of all inductive subsets of R. Inductive subsets of R. You see, very interesting phenomena is stating here. Look, natural number set. It is said now we define the set of natural numbers as an intersection. Of A from subsets of R such that A belong to I. Belong to the I. What is the I? I is inductive sets. So if I is the inductive sets and capital A is the element of capital this A, and A is a definitely R is the largest subset in R. You know, in the real line number set, R is the largest set. But we here the is a natural number set can be considered as an intersection of all A subsets of R such that A belong to the I. I is the inductive sets. So you see this one, if you consider you know, any subsets of R, a subsets A of R such that belong to the I is the inductive sets, then if we consider the intersection of all this collection of inductive sets, we get natural number set 1, 2, 3, and etc. and so on. So we will get this set, which is n. You see, usually we write all the natural number sets right like this. Now there is another form of the writing of the integer sets in the form of the intersection. Okay, please pay attention. We define the set of integer natural numbers as the intersection of the inductive subsets of R. That's like this. In other words, n is the smallest inductive sets. On the other hand, n is the smallest inductive sets in R. Because you see, A is a subset of R, and A belongs to the I. I is the inductive set, and inductive set is defined from the above. If if one belong to R A, then A plus 1 also belong to A. Okay, so that's why you see, generally this is very heavy writing of the natural number set. But if we define all the collection of this intersection point, then we will get this, which is n. Hey, still the students coming in, huh? I told you after 15 minutes don't come in. I don't know, maybe they out and come in again. Okay, I hope you understand. In other words, n is the smallest inductive set in R. This is in line with the intuitive idea that, you see, in other words, look, this 1, 2, 3, and so on can be written in this form. 1 is 1, 2 is 1 plus 1, 3 is 1 plus 1 plus 1, and so on. So any integer number can be written as the inductive form. You see, A plus 1. For example, 3. Actually, 3 is 2 plus 1. 4 is 3 plus 1. Also can. You see, according to this, if 4 belong to the A, then A plus 1 belong to the A. So if A is 3, then A plus 1 is belong to the A. So 4 is also belong to the A. Okay, so as a consequence, we obtain the following results. Commonly referred as, you know, what we call it? The principle of mathematical induction. Actually, on the other hand, this inductivity leads to the mathematical induction principle, the principle of mathematical induction. So what is the difference between this and that definition? Here, in a subset A of R is called inductive if two conditions satisfies. So here it is said if A is a subset of a natural number set, satisfies these two conditions, then A equal to n. You see? So the above definition, if I change little bit, it becomes like this. So the definition 1, you see, it is said, the first case, if 1 belong to the A, and second, A belong to the A, then A plus 1 belong to the A. So this is the inductivity. Now this theorem, TH, says if A is a subset of N. Now, exactly I choose, this is any A, N. And the two conditions, one belong to the A, and second, if N belong to the A, then N plus 1 belong to the A. So you see, I do exactly changing this definition with specific number set. Then if it is so, you see, if A is a subset of N and having these two properties, then conclusion says A exactly equal to N. It is a natural number set. Exactly coincides. Okay? So proof is also very, actually here very shortly, very easily they stated, but I try to a little bit describe more for the proof. You know what they use? They use the following tactic. When we say two sets are equal, if and only if A is a subset of B and B is a subset of A. Look, if A is a subset of B and B is a subset of A, then only the conclusion these two sets belong to the A. What does it mean this? What does it mean this? It means if we take any element from capital A, then we say this X is belong to the B. You see, any element, whatever, any element taking from the A is the element of B. We say the A is a subset of B. Now, the second one, analogically, we can say implies if we take any Y from B, then this B is also element of A. You see? From these two inequality, from these two subsets definitions, we can conclude any element from A is the element of B. Any element of B is the element of A. So it means they are equal. Okay, they are equal. So equal, they use this definition to prove this. Look, first of all, A is the subset of N, right? From the, okay, one moment. A is a subset of N is given. Now we will show that N is if this is given, then if these two conditions hold, then N is a subset of A as well. It is clear A is a first of all, look, first of all, since these two conditions hold this, A is inductive. It is correct. For the proof, you know, the first part. So A is a subset of N. Okay, this one is given. I want to prove that N is also subset of A. Okay, if N is a subset of A, this one is given. So it means these two sets are equal. So equality comes from that. Okay, now this one is given. Now I'm going to prove this. If A is a subset of N and A satisfies these two conditions, A for the A, two conditions hold, 1 and 2, which is implies A is inductive. Inductive, A is inductive. Now, if it is inductive and is it satisfying these two conditions, look, 1 belong to the A. So if I take the n as a n equal to 1, then n plus 1 becomes n plus 1 equal to 2 and belong to the A. So now if n equal to 2, then 2 plus 1 equal to 3 belong to the A. So you see, 1 belong to the A, 2 belong to the A, 3 belong to the A, and so on, so on. Any n, any m belong to the A, m plus 1 belong to the A, which implies it contains all n. It means the n is a subset of A, because you see, because A contains all the natural numbers. By this definition, it contains all the natural numbers. It means it contains n as well. It contains n. So from this two inequality, you see, A is subset of n, and n is a subset of A, implies A equal to n. Okay, n. So you see, if A has this form, then A is natural number set. Can I say, just according to this definition, can I say, okay, these two condition holds, one belong to the A, and second one, A is belong to the Q, rational number set belong to the Q, and A belong to the Q, and I say it is a subset of A, then A plus 1 belong to A. You see, if I'm just trying to say, if A set A satisfies this, having these two properties, can I say A equal to Q? A equal to Q. Of course, at the beginning, I have stated if A is a subset of Q and satisfying these two conditions, then can I say A equal to Q? I think for this case, I'm taking any integer number. So I currently I cannot conform because you see, A belong to the to A actually. A belong to the A. This two inequality belong to the A implies this subset of Q. So any A from A is a subset of Q, then these two conditions hold. So how we show that, here we have to show Q is a subset of A. If we are able to show Q is a subset of A, yes, then we can say A equal to Q. But this one is a problem. I don't know. Okay, anyway, so just here I am, you see, just trying to change. That is the analysis, that is the real analysis actually. You see, little changing the problem leads totally different results. Okay. Sorry, I forget today my glass. Now it is okay, much more better. Okay, anyway, So this this one is a problematic. Please, you think? I don't think so. This one can be proved. Okay, this is my suggestion. Please, if you are able to prove, let me know. So now next is what? We say that any inductive subsets of n is n itself. Just say that any inductive subsets of n is n. Okay, this is the conclusion of this theorem. This is the conclusion of this theorem. Any inductive subsets of n is n. Okay, now if we have this exercise, how we can prove? If two numbers belong to n, natural number set, then m plus n is also belong to the n. M times n also belong to the n. That is, n is closed under addition and multiplication. You see? In other words, the n is a closed. N is a closed under addition and multiplication. So, how we can prove this exercise or the preposition? Actually, this one can be stated as a preposition, and here it is given as an example. Actually, it is a preposition. Okay, let us try to solve it. According to this, m, if m n belong to the n, means of definitely one of them, since both of them is n, so I can say it is belong to the n. This is correct. This is correct. And here, usually, they construct A. This is a very important construction, as I understand. So A is a set of n such that m plus n is also belong to n. Okay, let capital A be the sets of natural number set such that m plus n is also belong to the A. Okay, so this is our new set, which is very important, and this one helps us to prove the theorem. Okay, if n A is taken as such a set, then of course A is a subset of n. It is clear, because n is the largest natural number set in among the natural number sets. So we can, imagine, look, how we take the inductive but subset of n. Look, if I take like this n from capital N, what is this set? It is the set of 2, 4, 6, and so on. Definitely, it is a subset of n, right? It is a subset. Or 2n plus 1, all the odd integers. Or I can say B is 3 times n. 3 times n. And n from capital N also is a subset. This is also subset. Inductive. You see, all of them are inductive subsets. Inductive subsets. So that's why, since n is a greatest set of natural numbers, so any set constructing in this form, for example, B, I can say is a set of M from capital N, such that M times N belong to the N. Okay, this set is also subsets of N. So the first part automatically comes if clearly, if A is constructed in this form, clearly A is a subset of N. Next, we will prove that A is inductive. If A is taken like this, we will prove A is inductive. If A is inductive, then it is equal to N according to the previous previous statement. Any inductive subsets of N is N according to this. So that's why please pay attention. So once we construct A like this, and it is a subset of N, clear. Now we are proving that this A is inductive. If it is inductive, then N is a subset of A. So since A is a subset of N and N is a subset of A, then we can conclude A equal to N. A equal to N. But here we are trying to prove that N is a closed under the addition. If we take any two numbers from natural number set, then by adding these two integer number set, we will get integer number set. So we are trying to prove that it is closed. So that's why I think here it is not going to state that N is a subset of A. So, but it is in the they are trying to say that A is an inductive set. If it is chosen like this, it is inductive set. How we prove? Proof, you see, now not taking just element 1 to prove the inductive. So they try to prove this way. So look, once again, A in my case is taken as all natural number set such that M plus N also belong to natural number set. You see, whenever N taking from capital N and adding M also belong to the N. So this is a new constructing set, and we are trying to say that this is an inductive. Okay, how to show? Since y M plus N, okay, N from capital N, M plus N. So M plus 1 by definition. Okay, can I say it is, look, M plus 1 belong to the N by definition N. Okay, so I am taking the M plus N. You see here, because look, if I am taking 1, yeah, please pay attention. If I'm taking 1 from N, then M plus 1 is belong to the N. You see, when N equal to 1, according to this definition, M plus 1 belong to the N. If M plus 1 belong to the N, then according to the definition, 1 belong to A. 1 belong to the A. You see, here I'm not saying that 1 belong to the A, then N plus 1 belong to the A. Here, by this definition, so by taking N equal to 1, I have shown 1 belong to the A. Okay, second, 1 belong to the A. Now, if N belong to the A, then N belong to the capital N, such that M plus N belong to the N. And by definition of N, this one belong to the N. Why is it the product? Okay, you see the little bit difficult statement, but now I understand like this. So since 1 belong to the A, now we are taking for the second case. So look, since A is this set of such kind of sets, so it means if I take N from A, from A, from A, then of course n belong to capital N, because A is a subset. A is a subset of N. So if I take any N from this set belong to the A, definitely it belongs to the N, correct? Such that, because of definition, such that M plus N also belong to N. You see? Why this one? Minimize. Okay. I minimize that. Please pay attention. This is the definition of A. Now, I'm taking N from A. Definitely, it belongs to the N, and because of definition, M plus N belong to the N is also we can make we can say that it is holds. This one in call it holds. Now, we are taking like this: M plus N plus 1. So because of associative property, we can write it as N plus 1. And you see, M plus N plus 1, because of this, it belongs to natural number set. From here, N plus 1 also belong to A. By the principle of mathematical induction, A equal to N. Then, by the principle of mathematical induction, A equal to N. Okay. What does it give? What does it mean? You know? Okay. So please pay attention. Now here they are trying to say, if A is taken in this form, it is inductive. If it is inductive, it contains N. At the beginning, it was a subset of N. So since it is inductive, then actually A contains N. Look, 1, because of construction of the set A, I was able to find 1 belong to the N. Then if 1 belong to the A, then N plus 1 belong to the A, which is inductive. A is inductive. If A is inductive, then it contains N as well, contains A as well. So since A is a subset of N is a subset of A, implies A equal to N. A equal to N. So it means, you see, what is A? A is a set of N such that M plus N belong to the N. So from this inequality, we can say if N and M belong to the N, then M plus N belong to the N, which is closed and the addition. Now, please you prove. This is good exercise actually. Good exercise. Taking the B like this, and similarly show that A is the inductive. Actually, B is inductive, and therefore coincides with N. So second part you will prove. You see, you need to show if 1 belong to the B, the N plus 1 belong to the B. You have to show by using this type of set. Okay, I hope next week I will ask this one, how you prove. Did you understand general idea? You see, if A is taken in the form of this, then here it is shown that if 1 belong to the N, N plus 1 belong to the A, which means A is inductive. If A is inductive, then it is equal to n actually. So it means n, it contains n, and A is a subset of n. So from this we can say A equal to n, which means the first condition holds. So natural number set is closed under addition. So the second one, it is under multiplication. Okay, one more problem. I am just trying to state this preposition. I'm stating preposition like this. If same at the beginning, m and n belong to the n, then m minus n is also belong to n, belong to the n. And m times n is also belong to the n. Okay, look, if this one hold, then the subtraction and division is also belong to the n. And if it is so, then I can say this n is closed, n is closed, and the subtraction and the subtraction and division. And the division. Is this correct? Huh? Is this correct? Hello? You see, I'm analogically formulating the theorem. For example, if m and n belong to the n, then m minus n also belong to the n, and m over n is also belong to the n. That is, n is closed under subtraction and division. How can I prove? Proof, you know, in order to prove, you have to go all this structure. But this is not easy. But I hope you can say you should have objection that this statement or this preposition is not correct. Am I right? To disprove, you know, no need to prove. To disprove, give one example is enough. M minus n is belong to the n. M over n is not belong to the n. Can you give any counter example? Hello? Hello? Do you have any counter example?
For the division,
Okay.
let's say 3 over 5,
M equal to what?
then it will be a rational number, but it is not in n.
No. Should be integer number. M and n must be integer number.
Yes, I mean n is 3 and n is 5.
M equal to, just give one example. M equal to what? 1, for example.
n equals to 3. Yes,
N equal to
n is
n equal to
5.
5, for example. You see, both of them belong to the n, but it doesn't imply 1 over 5 is in the n, right? This one doesn't imply, because 1 over 5 is not n. Enough. You have given very good counter example. So you have given for the second part. So m over n is not belong to the n. Okay? You have disproved the second part. What about first part? Can you take same number, right? Same number, and consider m minus n. M is 1, minus 5 minus 4, which is not belong to the n. You see, which is with one number you can show that these two statement, two properties doesn't hold. You see, here we use the opposite counter example. You see, we are able to provide the counter example. Now, no need to prove. We can conclude that this statement is wrong. It's not true. Am I right? That is the approach, you know. That is a very nice approach. So first, always you try to look at the counter example for any statement. If you are not able to find, then okay, it must be conjecture. For the conjecture, we need the proper proof. For the proper proof, we have many methods: direct proof, indirect proof, contrapositive, or negation. So you see, we have many techniques to prove the statement. You see, for the first case, can I provide any counter example? Whatever you take any two rational numbers, their sum is a natural number. Their product is a natural number. You cannot provide counter example. Now, so it must be true, but how to give the proper proof? So here, very nice proper proof. If A taken as n plus 1 belong to the n, you know, said like, and at the end proof A equal to n, so means this equality, this statement is true. Okay, that is a, you know, the proper proof. Actually, proper proof not easy. Counter examples sometimes easy to find, but for this case we cannot find. Okay, I hope you understand the main point. Now, after a few minutes, we go to the second example. Actually, this is preposition again. For any n, prove the following is, you see, if n greater or equal to, then nothing. Actually, after seeing that if n greater or equal to n and belong to the n, then the any n constructing in this form is equal to n. So actually this inequality belong to the n greater than n leads that natural number set. It leads the construction of all the natural number set. Here, if n not equal to 1, then n minus 1, but n belong to the n, but not equal to 1. Means n start from the 2. If n start from the 2, 3, 4, and so on, then the n minus 1 also belong to the n. This is the proof. But proof is very long, actually. Not easy, not very simple. So that's why proving actually is a problematic. Okay? But we have to learn. Okay, I will teach some of them. Some of them I will leave it for you. Okay, just 5 minutes. Relax, because I think too much already info. So today 59 students, except me, 58 students. Actually, how many students registered this time? I saw 71 students. Now, I think getting less, I think, huh? Another 11 or almost, you know, 12 students not attending. But please pay attention. This subject is not easy subject. Pay attention. Next week we have the first quiz. Okay, please register. Never mind. Okay, I hope the other students already done. Okay, so now let me share the screen again. Okay, let us continue our journey. Actually, now we have to accelerate because now just the first one. How we prove if n belong to the n and n is greater than okay. So I want to prove this preposition. Preposition, just preposition. One. Let n belong to capital N, natural number set, and n greater or equal to 1. Equal to 1. Then so greater than 1 implies natural number set. So we will get whole natural number set actually. Under this condition, we can get whole natural number set. Proof. So you see, always we construct A according to this definition. It is a set of n from the capital N such that n greater than 1. And we prove this set is inductive. If it is inductive, according to the above theorem, it is equal to n. So that is the proof. So now, again, clearly, A is a subset of n, first n. And it follows that 1, you see here, n greater or equal to 1. So because of this definition, n greater or equal to 1, which means when n equal to n 1, so is the n, and that's why when n equal to 1, so this 1 is the element of A from this definition, n equal to 1. Okay, now the first the first properties hold already. N equal to 1 implies belong to the A. Now second, here you can see if n belong to A, n belong to the A, n belong to the A, according to this, so n should be greater or equal to 1 since 1 is greater 0, n plus 1 is greater than n plus 1 is greater than n plus 0, which is equal to n here equal to 1, greater than 1. So n plus 1 is greater than 1. So which implies n plus 1 is belong to the A. Okay. So if we understand this this statement, then finish. A is inductive. If A is inductive, it contains capital N. And since A is a subset of N, and N is a subset of A, implies A equal to N, which is natural number set. Okay, how to understand the second one? Please pay attention. So A is a set of N such that n greater or equal to 1. Okay. Now, if n belong to the A, which is satisfied this condition, greater than 1, and 1 actually is strictly greater than 0 is correct. 1 strictly greater than 0 is correct. Then we are adding both sides of this inequality n. Okay, look, 1 greater than 0. So we are adding both sides n greater if I say n plus 1, I cannot say that n plus 1 is greater. Okay, look. So this one is given, and n is greater than 1 also is given. This one also given. This one also given. So if I add, okay, look, if I add, look, this one, 1 greater than 0, n is greater than 1. If I add, you see, n plus 1 or 1 plus n is strictly greater than 1 plus 0. 1 plus 0, which is equal to 1. Plus 1 also belong to the n. You see, is because n plus 1 is greater than 1, satisfies this inequality, or another one is belong to the A. You see, this n plus 1 greater than 1 satisfies this, and it belongs to the A. So if 1 belong to the A, you see, 1 belong to the A from this definition, and n plus 1 also belong to the A. So this equality implies n plus 1 belong to A. You see, 1 belong to the A, n plus 1 belong to the A. It means it is an inductive set. A is an inductive set. If A is inductive set, from the above definition or the theorem or proposition, we can conclude that A equal to n. Okay, A is this set according to the definition. So this set becomes n. Okay.
Then, Doctor,
Yes.
the inequality sign in the notes are incorrect because here written
Which one not correct?
n plus 1 greater or equals to 1. The notes
Even this?
written, yes, is it incorrect? We should write only greater than without the equal sign.
Even strictly greater, Even strictly greater than n?
Yes. So,
But
but the
actually
notes
here,
got equal.
yeah, you are right, because you know 1 is strictly greater than 0. Even n is greater or equal to 1, but this inequality strict inequality. You are right. N plus 1 is strictly greater than n plus 0. No, not n plus 0, 1 plus 0. 1 plus 0, because here I am saying this is 1 plus 0, not n plus 0. Sorry, this is totally wrong. I am doing. You see, n plus 1 is. I think this one you understand, because look, 1 greater than 0 is given. N greater or equal to 1 is given. When I add these two, this n plus 1 actually strictly greater than 1 plus 0, which is 1. You see, so n plus 1 strictly greater than 1 satisfies this inequality this inequality? So it means n plus 1 belong to the A. Okay? N plus 1 belong to A. So if 1 belong to the A and n plus 1 belong to the A, it means A is an inductive set. If A is inductive set, it must be equal to n according to the above statement. So we have proved this. Now it is, I think now it is proper. Sorry, I put here wrong, n plus 0. No, 1 plus 0. Just look at this. So this one is more proper. So this inequality I properly showed here. Okay. So please, here look, number C, m and but please pay attention. M minus n belong to the n, but here m greater than n statement. You see, under this statement, m minus n belong to the n. So you need to construct the set A such that, so you know, here construction of the set A is important. You see, for the second case, why they are constructing set like this? One union. You see, one union of this set. Then at the end, they come up that A is the inductive. So and therefore n minus 1 belong to the n. So means this A is inductive. They are trying to say A is the inductive. In the number 3, this set m minus n. You see, please try to read and understand. So whenever A equal to n, you see, A inductive. How to construct A? So A is not just ordinary set. It is a special set, and this special set can be shown it is inductive. If it is inductive, then A equal to n. So every cases we are focusing on the inductive problem theorems. Okay, inductivity. We are trying to show the inductivity. Okay, I hope you understand. The rest I hope you can make it. So now next theorem. Any non-empty subset of n has at least has a least element. Okay, this one little bit difficult to prove, but you see, first of all, can I try to find the counter example to this for this theorem? Any non-empty set of n, any non-empty subset of n has a least element. I try to prove by finding the counter example. So I am taking, for example, a subset of n. For example, I can take even number set, so to n, such that n belong to capital N. So if I list down 2, 4, 6, and so on. So least or minimum, actually I can say infimum of A is equal to 2. Exists. Whatever I construct subset of n, please pay attention. Even here, I can say the set A is finite. Also can. For example, the B, for example, set B, I will construct such a way it is a finite, but it has least element. The B, for example, I can just take the 5, 2, 1, 10, 12. There is no order, but I have the finite, just finite number. Okay, 100, 100, and so on, just like this. So the infimum of P exists. Infimum of P is equal to 1. So it has in the least element. I cannot find any counterexample to the formulation of this theorem. So it means it is a conjecture. If it is conjecture, we need the proper proof. So how to give the proper proof? This is the proof. So we will take how to prove now. We will take just any subset of, so subset is denoted by S. So let S be subset of N. I'm taking any. And definitely S is not empty set. This one we can confirm. It is not empty set. How we empty set? We denote like this. It is not empty set. This is correct. We will assume that S. Now look here. The proof is we are using contrapositive method. Contrapositive method. For the contrapositive method, so here one student going to in. For the contrapositive method, S is non-empty, and S, here assume, it is better say assume, it is a subset of N, and assume S has no, what we call it, has no minimum. Has no minimum. And show that this leads to the contradiction. And this leads contradiction. What kind of contradiction we can come up? If S has no minimum element, and S is a subset of N, then we will come up that this implies empty set. You see, S, you see here, actually S is a subset of N, and S is not, here I can say this one not implies, and I can say N. S is not empty set, it is not empty set, but it's in the assumption I say S has no minimum element, then we should come the contradiction. Contradiction means, so we will at the end, if we come up A is an empty set, S is an empty set, so it is a contradiction to this condition, because any subset of N is not empty set. At least one element we have. Okay, so we will come up with this conclusion. How? Now you see again, construction of A is important. Let A is defined by this. It is a set of N. But you see here, this is not easy to construct and etc. N with intersection S is equal to empty set. Look, S is a subset of N and not empty, and this what we call it, finite integer number set with S is empty set. We define A like this. So it is exactly empty set. So why I write this one so A is a set of N such that this 1, 2, and etc. N intersection with S is empty set. Okay, you see, construction of this A is not easy. It's not easy. Currently, it is given, so therefore, we are taking this A. Now, why the I, case I, why it is said 1 is not belong to the S? If you see, if 1 belong to the S, then it has the least element automatically, because natural number set starting from 1 definitely has the least element 1. So now from this assumption, so S is a subset of N and non-empty, but it has no minimum. So if it is had no minimum, 1 not belong to the S. Otherwise, would be smallest element in S. By example 32A. 32A. What is a 32A? The previous example, it was 32A, huh? Because of this 30A. Okay, good. Hence, okay. Hence, 1 belong to the A. Why? 1 not belong to the S. You see, it is from this definition, 1 S is a subset and A is constructed like this, but the 1 is not belong to the S. Hence, 1 belong to the A. Why? 1 belong to the A. So here there is no 1 in the S, but intersection with S is empty set. So why can I say that 1 belong to the A? So this set intersection with S has no element 1, but why here I can conclude that 1 belong to the A? If S doesn't include 1, and here pay attention, this one, all this intersection set is empty. It means if S contains empty, so S cannot contain 1, 2, 3, and etc. n. So all this natural number set is not in the S to be empty, this to be empty. So S doesn't contain any element of this. Otherwise, it will not be empty. So all this empty. Why here 1 is not in S? Correct, will be smallest. Hence, 1 belong to the A. Why 1 belong to the A? Why? Because here it is called, if it is not empty, then I can understand. But here 1 belong to A. To be belong A, intersection should have element 1. Intersection empty. All the element with S, this intersection is empty. It means S doesn't contain 1, 2, 3, and etc. n. None of this element doesn't contain it in S. Okay, so hence why A below A taking the A? This is a problem now. Can you imagine? Do you have any interpretation? The A is a set of like this, but Now, since 1 is not in the set S, but 1 belong to the A. Here we have intersection. S doesn't contain N. So if doesn't contain N, this intersection is empty set. Is empty set. Why 1 belong to the A? I didn't understand this. Let N belong to the A, then if K belong to the S, K cannot be like this. It is correct. Hence, K greater than N. Correct. Example 3 to D, K greater or equal to N plus 1. It is correct. Now, N plus 1 belong to the S. Yes. Then N plus 1 is minimum of S, in contradiction with our assumption. Therefore, N plus 1 shouldn't belong to the S. So, N plus 1 belong to the A. Thus, A is the inductive. If this intersection empty, okay, now I try to understand like this. Look, what about this A? If I describe A, look, N belong to the N, capital N, such that 1, 2, and etc. N intersection with S is equal to MT, means, please pay attention. What is this N actually? This one, as I understand, if MT, so A will very interesting. And up to N intersection with S is empty set. Intersection with the S is empty set. Empty set. So if S contains N plus 1, N plus 2, and etc., then this one implies, so is contains N plus 1, N plus 2, and etc. So, you know, all the empty. But what about A? If S is N plus 1, intersection with N, empty set. N plus 2, empty set, and so on. So, this implies that. But how can I say that element 1 on the other hand, you see, from here, it consists of all these element intersection with S. So it means it contains all the element of 1, 2, and N, because this one is belong to the A. But intersection with S is empty. So A actually has a set. From this definition, I can say A is a set of 1, 2, and up to N. Because intersection with S, empty set, when S, N plus 1, N plus 2, and so on. So, from here, I can say the 1 belong to the A. And I can say if can I say N plus 1 also belong to the A? How can I state it? N plus On the other hand, look, actually, now we should understand like this. Actually, S can start minimum n plus 1, n plus 2, and etc. But if S consists of this element, then list element exists. List element exists. According to the assumption, S has no minimum. S has no minimum. So if S no minimum, look, if S has no minimum, then n plus 1 also not belong to the S. If n plus 1 not belong to the S, then it belongs to the A. Okay, so we should understand like this. You see, because it is because of assumption. You see, we are saying S is a subset of N, and S is not empty, but we are assuming that S has no minimum. If S has no minimum, it cannot start from N plus 1. So means N plus 1 doesn't belong to the S. If doesn't belong to the S, then actually it should be added to the N. Added to the N. So N plus 1 also belong to the A. So if 1 belong to the A, N plus 1 belong to the A, then A is inductive. If it is inductive, then A is equal to N, right? A is equal to N. So therefore coincided with the N. But this implies S is the empty. Look, very nice actually the logic thinking here. Please pay attention. N plus 1 not belong to the N, but N plus 1 belong to the A. N plus 2 also not belong to the S, and opposite N plus 2 belong to the A. If this way, if I continue, you see, actually already here I stated A is equal to N. If A equal to N, then this S should be empty set. But according to this, it is not empty set. I come to the contradiction. You see, slowly I removing all the element of S. Look, at the beginning I say, since this one empty, S should be like this. S has the element n plus 1, n plus 2, and so on. But at the end, I come up with the contradiction. Okay, so now tomorrow we will continue, and we will have very important statement, which is call it in the principle of mathematical induction. So if we learn this principle of mathematical induction very well, many problems we can settle well and prove well, easy way. Okay, so very interesting topic we are stopping. So tomorrow, inshallah, I will complete this and some interesting examples. Then completeness axiom. After completeness axiom, actually we can finish this chapter actually here. Now I do accelerate. Tomorrow, inshallah, I will finish. Okay, next week we have exam. Finish. So already 11 o'clock and many students already leave. No problem. Okay. I hope no questions. Currently, it is interesting and easy. Well, not easy, but it is interesting. Thank you.
Doctor, how
Question?
about the quiz? Just now, doctor mentioned quiz face to face, is it?
Actually, not face to face. Just online during the class time. I will give for half an hour.
Oh, okay,
Okay.
doctor.
But not on Sunday, on Monday. For any case, Sunday we will do some revision Actually, already I told from where I will take. Mostly, I will take from the secondary lecture notes. But from these lecture notes, I will also take just two examples. I will choose 2 or 3, maximum 3. Otherwise, 2.
Okay, doctor. Thank you, doctor.
Thank you very much, and see you tomorrow. Okay. Bye bye.